Hi everyone, so in this video I'm going to talk about the definition of a matrix space along with some examples. So let's get started. Given 2 points A and B in R2, recall that the Euclidean distance between A and B is the square root of the quantity A1 minus B1 squared plus A2 minus B2 squared. However, imagine that you travel in Manhattan, New York City on a taxi cab. Then to go from point A to point B, you can go from A to C and then from C to B. Alternatively, you can follow this path. In either way, the total distance you travel is not the Euclidean distance between A and B. So how can you compute the total distance you travel? First of all, observe that the length of this side of the triangle is the absolute value of A2 minus B2, and the length of this side is the absolute value of A1 minus B1. So the total distance you travel in either case is the absolute value of A1 minus B1 plus the absolute value of A2 minus B2. For any 2 points A and B in R2, we define the Manhattan distance between A and B by this formula. Then D1 is a function from the Cartesian product of R2 and R2 to R. Even though the Manhattan distance doesn't share all properties of the Euclidean distance, it satisfies the following properties. And mathematicians capture all these important properties to define a matrix and also a matrix space. So I'm going to talk about that in the next slide. Let X be a non-empty set. A function D from the Cartesian product of X and X to R is called a matrix on X if the following conditions hold for all elements A, B, and C in X. The first condition is DAB is non-negative and DAB is equal to 0 if and only if A is equal to B. The second condition is the symmetry. DAB is equal to DBA. And the third condition is called the triangle inequality. DAC is less than or equal to DAB plus DBC. If D is a matrix on X, then the pair XD is called a matrix space. And if no confusion occurs, we can simply say that X is a matrix space. Now, I'm going to talk about some examples of matrix spaces. In Rn, we consider 2 elements A and B, and then we define DAB by taking the square root of the sum of AI minus BI squared for I from 1 to n. And we define D1AB by the sum of the absolute value of AI minus BI for I from 1 to n. We can also define the infinity of AB by taking the maximum of the absolute value of AI minus BI for I from 1 to n. Then we can show that D1 and D infinity are 3 matrices on Rn. In the next example, we are going to define a matrix on the set of all continuous functions defined on the closed bounded interval 0, 1. Given any 2 elements f and g in C01, we define dfg by taking the maximum of the absolute value of f of x minus 3 of x, where x runs into this closed bounded interval. The function d is well defined because of the extreme value theorem, saying that any continuous function attains its maximum on any closed bounded interval. Then we can show that D is a matrix on C01 and C01 with D is a matrix space. It is very interesting because at this point you can compute the distance between 2 continuous functions defined on a closed bounded interval. And consequently, you can define the notion of convergence along with many notions of analysis based on this matrix. Okay, finally, I'm going to talk about 2 more examples. The first example is a rather weird matrix defined on an arbitrary set X. Let X be a non-empty set. Given any 2 elements of X, we define DAB by this formula. It is 0 if A is equal to B and 1 if A is not equal to B. We can show that D is a matrix on X and it is called a discrete matrix. Finally, given two elements A and B in R, we define DAB by taking the square root of the absolute value of A minus B. We can show that D is a matrix on X. Later on, we're gonna talk about the notion of norm on a vector space over R or C. Then we can show that D cannot be induced by a norm. Okay, so we're gonna talk about that in our future video. So let's wait for that. This completes my video on matrix spaces along with some examples. Thank you for watching.